The diversion from the main story took us to discover an uncertainty rule. Now we come back to our original task of characterizing the unique solution of the P0 problem. More specifically, and still considering the two-ortho case, we ask whether we can guarantee that a solution is unique, and whether we can suggest a practical algorithm to find it. We start by stating the uncertainty rule we have just proven. For a pair of ortho matrices, we can compute their coherence. Then we know that the sum of the number of non-zeros in alpha and beta, both representing the same signal, is lower bounded by 2 over mu. Assume now that we are looking at the underdetermined linear system Ax equals b, where A is the amalgam of psi and phi. Suppose that we get two different candidate solutions for this system, x1 and x2. As we are about to show, another uncertainty rule applies here, this time on the sparsity of x1 and x2. Taking these two linear systems with the solutions of x1 and x2, we can subtract them, getting that x1 minus x2 must be in the null space of A. Put differently, we can take the vector x1 minus x2 and divide it to alpha, the top n entries, and beta, the bottom n ones. Thus we got the relation psi alpha equals minus psi beta. Note that these two vectors are necessarily non-zero, since x1 minus x2 is non-zero. Well, this is exactly the case we have covered by the uncertainty rule, and thus we know that the sum of the non-zeros in alpha and beta must be bounded from below as before. However, summing the number of non-zeros in alpha and beta is exactly the number of non-zeros in the difference vector x1 minus x2. Furthermore, we have mentioned before that the L0 norm obeys the triangle inequality, and thus this count is upper bounded by the sum of the non-zeros in x1 and x2. This leads to this inequality that says that any two solutions of the underdetermined linear system cannot be jointly sparse. Here we pose this statement as a theorem. x1 and x2 are two different solutions of the system Ax equals b, and A has a two-ortho structure. Then the sum of the number of non-zeros in these two solutions is lower bounded by 2 over mu. What about the proof? Well, we have just proven this property in our derivations. As an immediate consequence of this rule, suppose that we are given the problem P0 with the two-ortho structure, and we are offered the candidate solution x having below 1 over mu non-zeros. Invoking the above rule we have just proven, we can say that any other solution must have more than 1 over mu non-zeros. Well, that means that x is necessarily the sparsest possible solution of the system Ax equals b. Here is this statement posed as a theorem. A simple test of counting the number of non-zeros in X could tell us if this is the globally optimal solution of P0. Let's discuss the implications of this theorem. We are dealing with a special case where A is built as a pair of ortho matrices. For this case, we have a simple test for global optimality of a candidate solution. Think about it. Here we are trying to solve a very complicated and non-smooth optimization problem that may have many local minima points. In such cases, one could at best check locally for optimality. And in this specific case, we are armed with a much stronger tool. On the downside, if a solution is sparse but not sparse enough, that is, it has more than 1 over mu non-zeros, nothing can be claimed. Also, we cannot guarantee the existence of such a sparse solution to begin with. Lastly, I remind you that all this is true for the two-ortho case only. So to summarize, we have posed some questions and now we have some partial answers. If a sparse enough solution is found, it is unique. The test to verify that is the simplest possible, counting the number of non-zeros in this vector. What about algorithm for finding it? We will get to this very soon.